Hello everyone. Uh, Welcome back to another walkthrough. And today we're going to be doing Friday the 14th of June 2019. That's more like it should be June. And this is the 2PR paper. 2PR physics paper. Okay, here's the formula that we need to learn. Uh, some of you may know these off by heart, which is good on you. It's better to know these off by heart, guys, so you can always answer the question with ease. Now let's get to the first one. The diagram shows a fossil fuel power station. 5 stages of electricity generation and transmission are shown. Furnace and boiler, condenser, turbines, generator, and transformer. The power station burns a fossil fuel in this furnace. Give an example of a fossil fuel. So guys, usually the fossil fuel is going to be here. It's what we're burning. The fossil fuel will be usually what we're burning. And I'm going to give the example of, most people would answer oil. And yeah, that's right. You can also say crude oil. That's also right. You can also say coal and natural gas. The examiner allows you to say petrol, kerosene, diesel, gasoline, probably heavy fuel. It was very, very similar. Yeah, you're allowed to say all of that as long as it's a fossil fuel. Which stage of the power station transfers energy from a chemical store to a thermal store? So this part, guys, when we it's in the boiler, well, the furnace, I should. What part of it's the furnace and which one? I'm just gonna put furnace and boiler. Yeah, guys, it's the furnace and boiler because if we zoom in real quick, let's say that this is a bunch of oil, right? Looks more like water now, to be honest. And when we set it on fire, the chemical reaction of combustion, would happen. Yeah. So it's between oxygen and whatever we're burning, probably carbon. So we're getting carbon dioxide, probably made out of carbon. So yeah, it will be the furnace and boiler because there's a chemical reaction going on in there. Combustion. Couldn't be the condenser, guys, because it's cold in here, and it's a physical change. It's just creating bonds, sort of, because our steam is going to turn the turbine. It's going to go through here, and then it can condense back into water. It doesn't chemically change. It's just going to be in a different form. It can't be the generator, guys, because there's not really anything happening apart from that it's the dynamo effect's happening. Yeah, and well, the energy is being transferred from the electrically from the kinetic energy store, and it can't be the turbines because well, it transfers energy from a thermal energy store, which is this guy. Mostly kinetic energy to kinetic energy, but this guy's thermal because it's speeded up, and then it goes into this turbine. So yeah. It can't be any of these, but the furnace and boiler. Which stage of the power station transfers energy electrically from a kinetic energy store? Okay, it would be the generator because of the turbines are moving, guys, and when the turbine is moving, it causes the generator to spin, and when the generator spins, in this is probably here, this part out here, this part between these lines, that's probably a magnet. So when this generator spins, it's going to experience a change in magnetic field and make energy, basically. So it's going to be the generator. Okay. Sorry guys, if my voice is very croaky, I have a really sore throat. I'm putting out on myself to make this video because I want to. Yeah. Okay. Electricity can be generated by solar farms. Energy is transferred from the sun to the solar farm by radiation. The solar farm uses, wow, photovoltaic cells. I've never heard of that before. That's cool. To transfer this energy electrically. Discuss the advantages and disadvantages of generating electricity using solar farms. Okay, guys, there's many things. Let's start with the advantages. I think it wants us to give us 2 advantages. So, advantage. Let's give all the points, guys. So it is renewable. Solar energy is renewable, at least for another many years, till the sun explodes. But we don't really need to talk about that. Well, I said what explode. It just turned enlarge and enlarge, engulf us, and then turn into a white dwarf. But you get my point. Um, it doesn't require fuel. Low running costs, basically. Costs, as it requires little, no fuel to work. And there are no greenhouse gas emissions. Okay, disadvantages. Well, that's a lot of lines. The sun doesn't shine all the time. Therefore, it's not really we don't really need to put this, but we can say that it's not really reliable, because it's not really a reliable energy source, because the sun doesn't shine all the time. You know, it requires it depends on the weather. It's dependent on the weather. Don't say it's dependent on the weather, guys, because that answer gets ignored. You need to specifically tell the examiner that it's because the sun doesn't shine all the time. The amount of energy output depends on the geographical, is that how you say it? I don't know, geographical location. So if you lived in Norway, for example, or Sweden, all those no, I think Sweden's better. If you're all the way up there, it's going to be very dark most of the time, especially Greenland and Iceland. But you barely see light, so it would never be a great idea to use solar panels. Another one would be it there are it requires large open spaces. There need to be, and what that means basically is that there needs to be a lot of them to produce a lot of power, and therefore you need a lot of space to let's say that we have all this this guy, and we could use this for farming. We could use this for farming, guys, but no, we're not using this for farming. No, we're gonna use this for energy. So how many solar panels are we gonna need? A lot. And we can't really optimize the space by putting my solar panels on top of everything. No, that doesn't work like that. Anyways, it's not very space optimal, let's just say that. Okay, so this question is about sound waves. Sound is an example of a type of wave. State this name of the type of this wave. Okay, guys, so you remember that there's transverse, and the next wave is longitudinal. That's the next wave. It's a longitudinal. That's all you need to say. The speed of sound in liquids is greater than the speed of sound in gases. Describe the arrangement of particles in liquids and in gases. Oh, that's interesting. You may use a diagram to help you. Okay, I'm sorry. You can draw it if you want. I'm going to try, but it's not going to be great. At least it's in like gases. Oh, this is in gases, guys, and this is in liquids. Supposed to look a little bit like that, at least. They're all supposed to be the same size, and same shape, but you know, it's not too easy with this mouse. Okay, so what we need to say, guys, let me just drink some water real quick, because we can say that. So, actually, you don't need to write anything if you did the diagrams like this. I think the examiner would understand what you're talking about. You're allowed to get full marks for just writing, clearly stating the differences in the diagrams, but I'd write it just in case anyways. So in gases and liquids, oh my gosh. Okay, in gases and liquids, the particles are arranged and in an irregular. irregularity, or irregularly, or you can even say randomly. Then you can say particles in a gas, guys, are further apart than in liquid, and then put in brackets free to move. Are further apart and free to move. Than in liquids. Okay, that doesn't make sense, but you get the point. Okay, particles in a gas are further apart than liquid, and in gases and liquids, the particles are arranged irregularly. I think it's better to label these diagrams: gas, liquid. Okay, let's go down. Suggest why the speed of sound in liquids is greater than the speed of sound in gases. Okay, so the speed of sound in liquids, because sound requires mass. It requires matter, because sounds, as long as you know waves, they work with matter. So they work with vibrations. So sound waves travel by vibrations, and when it's kind of hard to explain that vibrations are passed on more effectively when particles are closer together, because you know how in conduction, at least this is how I view it. In conduction, particles need to be close together, because if one vibrates, then the other one doesn't. One vibrates a little bit, then the other one will vibrate a little bit. But if one is far away, it needs to vibrate a lot for the other one to even have an effect on the other one, the other particle. So we could say that sound waves, the vibrations depend on the vibrations are passed on more effectively when the particles are close together. Hence, why sound travels faster in liquids rather than gases. There you go. Oh, sorry, my throat is starting to hurt a lot. I think we can do this, guys. Okay. A buzzer in an electrical device that produces a sound. Oh, okay, that's what they're saying. The frequency of sound produced by the button is 1,400 hertz. Speed. Okay, so I think they're trying to trick us, guys. It's not exactly speed, or at least that's not how I learned it. It's v, velocity. So let's just write the abbreviated version, because I don't have an in pen, because I don't actually have the lambda. And I'm not writing wavelength. Oh my god, that's too big for my writing of a word. So v equals frequency times wavelength, or lambda. Remember, guys, that I think it's actually, is it up here? No, it's not. I think I even stated that at the start. Okay, yeah, that's the answer. Sound travels at a speed of 340 meters per second in air. There we go. So 340 equals, calculate the wavelength, equals 1,400 times lambda. Okay, so now what we're going to do, guys, is we're going to have 340 over 1,400. Now, I know it's a really small number, but wavelengths are usually small numbers, so we've done it right if it's like this. Okay, so 340 divided by 1,400 equals 0.2428. It's really a lot of numbers. So basically just 0.24 meters. To be honest, that's not that small of a wavelength. That's basically just 24 centimeters. Okay. Oh my goodness, what's this? What is she doing? Oh god, they're wearing goggles. Two students use this method to investigate sound from a moving source. Doppler effect. Okay, guys. Student A connects a piece of string to the buzzer. She spins round so the buzzer moves in a horizontal circular path. She spins round at a slow speed, then spins round at a high speed. Student B stands several meters away from student A. This is kind of dangerous, guys. The sound heard by student A is different to the sound heard by student B. Discuss the differences in sound heard by student A and student B. Guys, this is a pretty hard question. So, when the buzzer, guys, moves away from student B, it's going to, when it emits its wavelength here and then goes here and emits it again, the wave is going to have a greater wavelength than if the buzzer was held here. It was going to have a wavelength, let's say, of this. But now it's moved while it's doing its wavelength. This guy's going to be dragged behind. But when this guy moves towards where it is emitting its waves, it's going to get even really, really like small wavelength. And the smaller the wavelength, guys, the higher smaller the wavelength, the higher the frequency. So this was going to be high pitched, and the lower the wavelength, the lower frequency it is. So the not quieter, the lower pitched it is. So we can also say, guys, that as sound travels, its amplitude becomes even smaller. So it becomes smaller and smaller. So its amplitude is basically the loudness of the buzzer. So the buzzer will definitely be louder to student A than student B. We can write about that. And because student A is student A, they're always constantly kind of the buzzer is never really going away from it. So the buzzer will always have the same pitch to student A than student B, because remember, student B is going to be experienced lower than higher frequencies of sound waves of the buzzer. Then student A is going to be just hearing the same one over and over again. So yeah. So yeah. Oh yeah, and we should also talk about when she spins at a slow speed, she won't notice much of a difference. Though when she spins around at higher speed, student B will notice more of a difference. Okay, we have a lot to write about here, so let's write. Okay. So let's talk about loudness first, because that's easier. The sound heard by student B will be louder. We don't need to explain why, guys, because I explained why. Student B will hear the sound in different loudnesses. The loudness at varied loudness as it moves away and towards her. Yeah. I think that's all that is for loudness. The buzzer. Wait. Student A will hear not here, will will hear the sound at a constant pitch. She will, there will be no change of sound for her when speed, no, we'll talk about the concept, we'll talk about speed later. Student B will hear the pitch change as the buzzer moves away from her. It will it will lower in pitch away, right? Yeah. And when it moves away towards her, it will increase pitch. Okay, what's next? When the buzzer moves faster, the difference in sound, no, in pitch basically, will become greater. However, to student B. However, student A will not experience any change. Okay, that's a perfect answer, guys. Definitely didn't use as many lines, probably because this text is pretty small, but also probably because they give you a lot of lines because they expect you to well, most normal people, they don't expect you to like write in full sentences, but most people would probably write in full sentences. So what we made it easier for the examiner, and we just bullet pointed it. The sound heard by student B will be louder. Student B will hear, oops, not student B, A will be louder. Student B will hear the sound at very loudness as it moves away and towards her. Student B will hear the sound at a constant pitch. Student B will hear the pitch change as the buzzer moves away from them. It will lower in pitch, and when it moves away from her, towards her, it will increase in pitch. When the buzzer moves faster, the difference in pitch will become greater to student B. However, student A will not experience any change. Now, this is actually worth 7 marks. All of these points is 7 marks. Sorry, that was a cough and a talk. So this is 5 marks, but we write 7 things here, so that's cool. Ah, wow, okay. Static electricity. Imagine that. Oh, wow. This thing is, yeah, I've not seen this in ages. Okay, let's see. The student charges a plastic rod by rubbing it with a cloth. The rod becomes negatively charged. Which statement explains how the rod becomes negatively charged? The rod gains positively charged electrons. Well, that's right, because electrons aren't even positively charged. Loses positively charged electrons. Well, it can't be any of these because they have positive, something that's impossible. The rod gains negatively charged electrons. The rod loses negatively charged electrons. It should gain, guys, because the rod is kind of scraping up the electrons of this cloth, and the cloth is becoming positively charged because the less electrons it has, the more positively charged it becomes. Okay. Oh man. Describe how the student could demonstrate that the rod is charged. Okay. Well, the student can put the rod near his hair, or if he doesn't have hair, guys, maybe he doesn't have hair, put the rod near small pieces of paper, and these pieces of paper become attracted to the rod. The rod move towards. You can, it doesn't have to be that. You can always say hair. I said hair. I didn't say hair because it was a example that everyone else says, and I want to be different. You can always say hair, and if the hair becomes attracted to the rod or moves toward the rod, then it proves it. You can do water. You can do another charged rod. You can use gold leaf, but I don't think anyone knows that. That is. So yeah, it's yeah, you can do whatever you want. Okay, the student, but guys, don't say anything, because if you said like a bottle of water, there's no way that's going to move. There's no way that's going to move. That is just too heavy. This rod is not a magnet. It's not a magnet. It's going to attract things because it has a very small difference of charge, a very small negative charge. It's not going to be strong. It's going to be very so if it's going to be very weak force. So if you're going to try and move like a whole car with it, it's not going to work. It's not going to work. Okay, so try to use really light things like small pieces of paper, water. Water can also do that because it's a liquid, guys. Only when it's running. Uh, maybe a little bit of cloth, maybe depending on how light it is. Okay, the student has several other rods. Oh wow, made from different kinds of plastic. Some rods can be charged positively and some can be charged negatively. Describe an experiment to show that different rods have different types of charge. You may draw a diagram to help your answer. Okay. So he has several. Okay. So what we want to do first, guys, is we want to make the rods. We don't want to make the rods like fixed. We don't want to have them like held from here and held from here. If that's so, then God, what are they gonna do? Like, they're. If you're trying to feel the force, it's not gonna snap together like a magnet, guys. I told you these again. It's really weak. This force. It's a pretty weak force. I would say really weak, but it's pretty weak. So, you won't really be able to feel much of a pull. But if you let it go here, then these guys will start to move towards each other like this. Maybe only slightly. Maybe you have to bring them a little bit closer, but yeah. So we want them to be hanging loosely. We want our rods to be swinging freely. We want first the student must hold the rods and make sure that they can swing freely. They must be brought close together, because if I brought it to like one side of the room, it's not like it's going to all of a sudden. Dude, if it was like a really strong magnet, maybe. But guys, remember, if something is really weak, then you gotta get really close to even feel it. Observation and we need to do an observation. So, the rods. Student. Oops, that's scary. Must observe attraction between rods and repulsion. Because if he only observes one, then we don't know if we can confirm that. Well, we kind of can, because attraction is between two oppositely charged, but I'm still going to say repulsion because I guess we want to check for variables or something, a control variable or something, if it's just in case it's not for some reason electrostatic attraction or repulsion. Oh wow, okay, a Hertzsprung-Russell diagram, interesting. I was not expecting this. Okay, this makes me really happy. The diagram shows three stages of evolution. Oh wow, that's a big question. Okay, describe the evolution of stars of similar mass to the sun. Okay guys, so okay, for this question, guys, and we are going to have to explain in detail, not just say the key terms, unfortunately, because We need to describe, guys. We need to describe the evolution. And we need to refer to temperature and brightness as well. So, yeah. So first, guys, we talk about the nebula. A nebula, which, guys, is, remember, a nebula is a cloud in space, which is made out of dust and gas. It collapses under gravity, forming a protostar. Guys, we can always bullet point this as the temperature of the nebula protostar, we should say protostar, increases. It increases, guys, because the particles, they're constantly colliding with each other. And you know, when you rub your hands together, it's kind of like that. When you rub your hands together, you're transferring your kinetic energy into thermal energy. So when this thermal energy increases, eventually, as the temperature of the protostar increases. So once it reaches around 300 degrees Celsius, 3000 degrees Celsius, then nuclear fusion can start to take place. And star, this protostar is now a main sequence. So after that, so we also can talk about how its mass, because it says temperature and brightness of stars in your answer. So how I'm guessing they want us to refer to how the mass of the star, the brightness of the star, the temperature of the star, the mass of the star determines on the temperature and brightness. Yeah, and then it does this for a long time, so we can skip all that boring stuff because well, there's nothing really that goes in between this. And then we go to once the hydrogen nuclei fuel runs out, the star enlarges and becomes a red giant. The star enlarges. Oh, okay. Red giants are brighter. They're brighter, but they're have a lower temperature than brighter and cooler than most main sequence stars. Eventually, the red giant contracts and becomes a white dwarf. So the white dwarfs are actually hotter than red giants, but they are less bright than red giants. It's weird, isn't it? But yeah, it's I guess it makes sense when you do A level. I guess, I don't know. That's what I'm hoping. White dwarfs are hotter than main sequence. They are usually hotter than most. I wouldn't say main sequences, guys. I'd say red giants and most main sequences, but not bright. As not as bright as main sequences. Red giants and main sequences. There, that's all 7, 8, 10 marks, wow. 10 marks, guys. we got 10 marks, but it's 6 marks, unfortunately. But, who said we couldn't get like 120%? I don't know what this paper is made out of, but I'm just saying. So, there we go. Man, my voice is hurting. Okay, next question. I didn't really talk much about this Hertzsprung-Russell diagram, to be honest. But okay. Okay, we'll be back. Stearic acid is a solid at room temperature, and it melts at a temperature of 69 degrees Celsius. I think I know what this is about, guys. Latent heat. Specific latent heat and specific heat capacity. You guys ready? I know you aren't. I hate it as well. A student investigate. Okay, a specific heat capacity. Okay, this is specific heat capacity, guys. Okay. Okay. The student starts heating the stearic acid at 130 seconds. Determine the time it takes to heat the stearic acid until it reaches its melting point. Okay, yeah. Its melting point is always going to be this this flat spot here, guys. Flat spot mean that it's using this energy not to increase the kinetic energy, but it's also using that energy. But now it's using that energy to break the bonds between the particles. So yeah. Okay, let's see. So we have to measure the time between here and here. What? Oh, I clearly did not. Sorry, I meant. Oh, no, there we go. Okay, here. It's that wiggly line. Okay, so we have, yeah, that will be 420. That will be minus 130. That is going to equal 290 seconds. Okay. The stearic acid gains 39 kilojoules of energy during the time it is heated to its melting point. Calculate the mean power of the heater. Okay, that's cool. So we're going to use the E equals PT equation because we have time, we have energy, and we're looking for power. So we're going to rearrange this to equals to the PET equation. I like calling it the PET equation because it literally spells out PET. And now we're going to be E over. Okay, so I want to convert this into joules. So I'm going to just times this by 1,000 so we can get 39,000 joules. And then we're going to put 290 underneath this. And then let's just use the calculator, guys. And there. That equals. Don't worry when it says mean. By the way, guys, it doesn't really want you to calculate it like 6 times and then divide it by 6. No. It just wants us. It's basically like we call this average. And this is incredibly dark here. I don't know why, but I can read it. That says 134. I'm gonna say 134, and I'm gonna say watts. Watts. Yeah. 334 watts. Okay, that's what it is. The mass of stearic acid used in the investigation is 0.45 kilograms. The stearic acid gains 39 kilojoules of energy when it is heated to its melting point. Calculate the. Okay, guys. Here's my equation. So, what's this equation again? It's actually at the top of the paper if you want, but I'm gonna try and use my memory. So, here's my equation. I think it is enthalpy change. I call it enthalpy. I like making it enthalpy, guys. You can always use the physics version, but I like using enthalpy because it makes me sound smarter. Plus, it's a chemistry thing, so it's better to strengthen that, strengthen my own thing with enthalpy. Okay, enthalpy change equals mc delta T. So we have we have this, We have this. We're trying to find the specific heat capacity. What's our temperature? Here. That's our temperature. Okay. So, we're going to do uh, C equals 39,000 over mass, which is 0.45 kilograms. We're going to convert that into grams. So that's going to be 40, 450, sorry, times, let's see, what's the difference? That's the difference in temperature. 22, oh gosh, like about 69? I'm going to say 69, guys. Okay, sorry, what the heck? 69 minus 20. So 49. Um, so, oh, guys, sorry. This is physics. It's physics, guys. Don't times the, this is physics. Keep the joules the same, guys, but it says again, per kilograms degrees Celsius. My mistake, my mistake. Don't times this by 1,000. 0.45, there we go. Okay, that's more like it. Yeah, I make a lot of careless mistakes. I need to learn from that. Okay, so I got 1,600. What the heck? 1,768. I'm gonna put 1,769 because it's got 0.7. So yeah. Also, if you look at mark schemes, usually you see that they want you to answer the question to round it to like 1,800. The answer on my mark scheme would be 1,800, but but I like to do this anyways. You can round it to 1,800 if you want, but I like to do this just in case because sometimes I'm a little bit scared of how answers. They want me to answer my question. They always accept you giving too much, so it's okay. Let's go down. Oh, transformers. Okay. State the name given to this type of transformer. Okay, guys, there's a step down and a step up. So if it goes like this way, guys, think of it as stairs. So if this has more coils, if we extended all these coils, so it's like this has more coils. Turns, they're called turns. This coil has more turns. If we extended the coil, and so it's got the same space around these, it's gonna be really big, basically. And then compared to this. So if you were stepping, guys, like this, you'll be stepping down. This is supposed to be human, guys. So that you'll be stepping down, right? So this is a step down. That's not actually how I think of it, but if you need some help on understanding, then you can always think of that. Okay, this is a step down. Step down. Transform. Okay. The student investigates the effect of changing the number of turns. Wow, this is a big okay, so just how the student can improve the reliability of his investigation. Okay, apply constant maximum voltage to a primary coil within 1,200 turns. Oh my god. Is he actually going to do 1,000? Okay. Use a secondary coil with 100 turns. Okay, I think what I love about this is that reliability is always on your side for these questions because you can literally say for every single one of them, he could repeat the experiment to find a mean. Literally that. So it becomes more reliable. If you want, you can say that. But yeah, that's kind of funny that you can answer that for every question and get it right, no matter how complex it is. Okay, these are the students' results. Draw these on. Okay. Okay, let's just do this. So, turns. This is for turns, like turns. voltage. Should be like this. Okay, like that, guys. It's not pretty, is it? 1.3 volts at 200 turns is going to equal to 2.5 volts. 300 turns, that's going to equal 3.8 volts. I don't think I have enough space for this. 400, 5.0. I definitely have enough space for this for, I did this on paper, but I guess not. 600, 7.5. There we go. That's not pretty, but okay. Yeah, that's what it should look like. Okay, so just how the student could improve the precision of his voltage measurements. He could increase the sensitivity of the voltmeter by allowing it to measure decimals places. Something like that. Or more. More decimal places. Okay. More decimal places. Okay. The student plots this graph to show the results of his investigation. The student plots one of his results incorrectly. Draw a circle around the incorrectly plot result. I'm guessing it's this one, guys, because it kind of breaks the cycle. Should maybe be a bit up here instead. Yeah, should be like that. It breaks the beautiful things, like a beautiful straight line. That's like 7.5. That's what he put in. But like, I guess so. Draw a line of, great, okay. It's supposed to be a line, guys. Oh gosh, that was, how did I mess up about that? Oh no. Whatever, your line should be like this. Yeah, it should be like, kind of like that. A bit straighter. Use a ruler, guys. I can't use a ruler. Describe the relationship shown by the graph. That, as the, well, it's a, there's a lot. As the number of as the number of turns increases, the voltage increases. No, I should say the output. And we should also talk about how it is voltage is directly proportional to the number of turns. We should say okay. The primary coil has 1,200 turns. Using the student's data, calculate the primary voltage used in his investigation. Oh no. Okay. What? Primary coil. Oh. Primary coil has 1,200 turns. I see. Okay. So Guys, we're going to use the equation. This one. And we're going to have 1,200 over, take any of these, guys. Take any of these, like, I'm going to use this one. 200 over 200 equals 3.5. VP over 2.5. So, what we're going to do, guys, is going to do this. 2.5 times 1,200 over 200 will equal to VP. VP will equal to 15. Primary voltage equals 15. That is nice. Okay. Okay, nice. Almost there, guys. Almost there. I think this is the penultimate question. Okay, so a game is played on a table with balls of different colors. I think this is cool, guys. The diagram shows the white ball moving across a flat surface. State the formula linking momentum, mass, and velocity. P equals mv. P is for momentum, guys. I have absolutely no idea why it is P, but okay. The white ball has a mass of 170 grams. Okay. We want kilograms, so we're going to do 170 divided by 100. Okay. Which equals to 1.7. So we have P equals mv. We were trying to find the momentum, so we're going to do 1.7 times v, which is 5.2. That equals to 8.84. What? No, that shouldn't. Sorry, error in my calculation. Probably screaming at me right now. Yeah, that's my mistake. Times 5.2 equals 0.889. No, I'm gonna say 0.9 because that's 8. It's 0.88, so I'm gonna put 0.9 kilograms per meter second. Yeah. No, let's put 8. I feel like that's not enough numbers. Okay. The white ball collides with a stationary black ball. The black ball has a mass of 160 grams. After collision, it's the same, right? That's weird that they have different. But okay. After collision, the black ball moves away from the white ball with a velocity of 5.0 meters per second. Calculate the velocity of the white ball before the collision. Okay, guys. So conservation of momentum. So how to do this? Okay, guys. So we have this momentum of our white ball, but now we need the momentum of our black ball. So what momentum do we have with the black ball? So we're gonna do P equals 5 times 0.16. 5 times 0.16 equals 0.8. That's a nice clean number. 0.8 is the because our white ball initially had a the velocity. It needs to be like the total amount of this needs to equal to 0.88 because we can't just lose momentum, guys, out of nowhere. So the total amount of momentum needs to be the same. So right now the white ball then will have 0.88 minus 0.8. It will have 0.08 momentum. So my white ball, it will be 0.08 equals V times its mass, which is point 0.17. So 0.08 over 0.17 equals 0.47 meters per second. That's the velocity of the white ball. Okay. During the collision, the white ball exerts a force of 80 newtons on the black ball. The direction of this force is to the right. Okay, to the right. State the magnitude and direction of the force the black ball exerts on the white ball during this collision. It should do the exact same to the left, though, because if this black ball could not exert the same force back at the white ball, then the white ball would kind of just phase through it. Like how a table snaps if you put too much weight on it. It will break because it cannot exert the amount of force that you're back. Okay. Oh, what's this? Photograph shows a device that can be used to ignite small pieces of combustible material. The device consists of a cylinder containing trapped air and a piston. Oh no. Oh my god. A small piece of combustible material. Okay, when the yeah. Okay. The piston is quickly pushed down at a distance of 145 millimeters. Well, the average force exerted on the piston is 42 newtons. State the oh, thank God. Thank God you said that. Wow, this makes it so much more obvious. Work done. We should probably put that as W now, not E. I like putting it as E because basically E. Then you see E more anyways. Force, FD. That's whatever. It doesn't matter. FS. I'd say FS because remember distance is supposed to be S, but I have a bad habit of having to put D. I'm putting D. It's allowed in the mark scheme, but I'm going to be wary. Some other tests they might not allow it, so yeah. Calculate the work done on the trapped air when the piston is quickly pushed down. So we're gonna have to convert this into meters. So divided by 1,000. We're gonna keep it as that. And we're going to force time distance. So this is gonna be this and 4.2. So what have we come up with? We have come up with 0.145 I'm so stupid. So this is going to equal to 0.145 times 4.2 equals 0.609. I'm gonna put all of those marks because it's a really small number. Okay, state the maximum amount of energy that could be transferred to the trapped air. Well, yeah, 0.609. 609. If it's 100% efficient, but I doubt it. Using ideas about molecules, explain why the trapped air heats up. Okay. The kinetic energy stored of the molecules increase. We need to talk about that because things heat up because the kinetic energy stored of molecules the overall kinetic energy store of a substance's molecules. As it increases, it heats up basically the substance. This is because we didn't explain why. Temperature in Kelvin is directly proportional to kinetic energy of the molecules. It's a thing that everyone has to say. This is because temperature in Kelvin is directly proportional to kinetic energy of the molecules. Yeah. The kinetic energy store of the particles increase, by the way, because they're closer together and they're bouncing off the walls more. So we should probably say that so it makes more sense. Due to the particles colliding with the walls and each other more frequently. Yeah. Yeah. That's why, guys. If I got you confused, I hope that makes more sense. Okay. Let's move that as well. There we go. Okay, last question. Suggest why the trapped air does not reach a high enough temperature to ignite the combustible material if the piston is slowly because well, we could say multiple things. The piston will have less kinetic energy to mechanically transfer to the combustible material as less work is done. Yeah. So yeah, hopefully that helped you. I think that's the end of the paper. Yeah. Hopefully we got 70 marks, guys. That was not an easy paper. But there we go. That is Friday, the 14th of June, 2019. Thank you for watching. How do I get off of this now?